I know that the other leg has to be, come on, man. You know it, I know it, we all love it. I hope that's true anyway. It's the Pythagorean theorem, or as the British would say, Pythagoras' theorem. Same thing. This video is going to take on the first 6 sections, but you'll see there's not, hopefully not too much there that you haven't seen before. So let's begin with solving x squared equals k. So this is yet a new type of equation. Previously we discussed linear equations, and then we saw absolute value applied to linear equations, and then we saw simple radical equations, which just became linear equations after we got rid of the radical. But this is something different. This is called a quadratic equation, and we'll come back to this in much more detail later on in the course. But quadratic is just what we call it when we have x squared. And there's a couple different possibilities for what the value of x could be in this case. So if k is a positive number, then we're going to say that x is equal to plus or minus the square root of k. So if we have like x squared equals 9, then we know that x is equal to plus or minus 3. If k happens to be equal to 0, then there's only one solution, and that's going to be x equals 0. And if k happens to be a negative number, so if we have like x squared equals negative 1, then we're going to say there's no real solution, because there's no real number that when we multiply it by itself, we could possibly get a negative, right? Because a negative times a negative is a positive. I've teased the idea of imaginary and complex numbers in a previous video, and that's really where this topic would go, but for the purposes of our course, we'll only be discussing real numbers. So for us, if we have x squared equals a negative, then we're just going to say there's no answer. And we've got 3 examples down below which are pretty straightforward. One of them I already kind of answered, x squared equals 9. That's going to have 2 answers, plus or minus 3. We just take the square root of 9. If x squared were equal to 13, then our answer is plus or minus the square root of 13. And I don't know what that is. It's like 3 point something, but this is a perfect answer. This is an exact answer. I don't like using decimals if I don't have to, because if I were to type in square root of 13 on a calculator, I'd have to round off the answer. So that's actually a less precise answer than just writing the square root of 13. And I say this because a lot of students that I've had in the past seem to really object to writing their answer in this form, but this is actually the best form. It's as exact as possible, so please embrace this. All right, and now I get to go back to something that I said back in chapter 4. So using the example of 9 again, there are problems where we have just the square root of a number and we're expected to simplify that. And I had said previously that that would be only the positive value. So this would be equal to 3, positive 3 only. However, when we have an equation, x squared equals 9, when we take the square root of both sides, we're going to get x equals plus or minus 3. So why is it that one of them only has one answer and the other situation has 2 answers? I don't really want to get into it. We're just going to say the simple rule that we'll follow is if we're solving an equation that has x squared equals, and we're solving for x, then we're going to have 2 solutions come out. If we're just dealing with numbers, there's no variable at all, and we're simplifying a radical, then we will just use the positive answer, the principal square root. Here's a few examples, and you're going to see that the process for all 4 of these is right up here. Step 1, we're going to get the x squared alone. Step 2, we're going to take the square root of both sides. And step 3, we're going to not forget the plus or minus. You should see in this a repeated structure. This is the same process that we followed for absolute value equations and radical equations, insofar as the first step was to isolate the absolute value, or isolate the radical, or now isolate the x squared. So we're getting the thing that's happening to the x alone. And then we do something that gets rid of that thing. For absolute values, we split it into 2 equations. For radicals, we square both sides. And for a for a quadratic, we're taking the square root of both sides. Right? So this is a pattern that is repeating itself through many different types of equations, which means that you don't need to learn really a different set of rules for each one of them. Instead, it's more efficient for you and for your brain to handle all this if you just look at the overall strategy that we're employing here, which is to get the special thing alone, and then we can do whatever is going to handle the special thing. Okay, and I should also just mention that, like I said, later on we're going to deal with quadratics in more depth, and so not every quadratic equation can be solved just by taking the square root of both sides, but everything that we'll see here can be, and later on we'll talk about when you can and when you can't. It's not too difficult to figure out when you can't do this, but we don't need to go there right now. So anyway, like I said, take a moment, read through these. In each one, we're getting the x squared alone as like a first step or series of steps, and then we're taking the square root, and then every single answer has a plus or minus. And we're into section B. Here it is, the Pythagorean theorem. A squared plus B squared equals C squared. Woo! Where A and B are just the two legs of a right triangle. It doesn't matter which one's which. Pictures aren't necessarily going to be drawn to scale, whatever. C is always going to be the hypotenuse. The hypotenuse is the longest side, and it is across from the 90-degree angle. I know that it's the longest side because we established in a previous video that the longest side should be across from the largest angle. And of course, if that's a right angle there, then the other two angles have to both be less than 90 degrees because the total is 180. Down below, we see kind of a more geometrical way to think about it. If I had a triangle with sides of A, B, and C, we can represent A squared as an area of a square with side length A, and B squared is the area of a square with side length B, and so on. And it turns out that if we take this entire area and add it to this entire area, the sum of those two will give us this entire area. So I always thought that was kind of cool. We can use the Pythagorean theorem to find the lengths of missing sides in triangles. I'm sure you know this. So in the first one, we have two legs. So we're going to solve 2 squared plus 3 squared equals whatever, x squared. And then we're going to solve the equation just like we saw before. We got the x squared alone, take the square root. In this case, do we include the plus or minus? No, because this is a problem that has a real context to it. It's not just an equation. It's about a triangle, and distances cannot be negative. So here we'll ignore the minus. On the right, now we have the hypotenuse and one of the legs. So we need to make sure when we write the equation that we write it correctly. In this case, we'll have x squared plus 5 squared equals 6 squared. The important thing, again, is that 6 is the hypotenuse, so that's got to be by itself. The order of these two does not matter because addition is commutative. We can add two numbers in any order that we want. So don't get hung up on which is A and which is B. It does not matter. Anyway, again, get the x squared alone, take the square root, and it's just going to be positive. Here's just two more that are a little more exciting. The one on top, you notice we have a variable in two places. It doesn't matter. Just use the Pythagorean theorem. We're going to have x squared plus 6 squared is equal to 2x squared. And then we have to use our rules of exponents from back in chapter 1. We need to square this whole thing. That's going to be 4x squared. And then combine the like terms, and then get the x squared alone, and then take the square root. And then we simplify the radical like we saw in chapter 4. The square root of 12 is the same thing as the square root of 4 times the square root of 3. And the square root of 4 is just 2. Down below, we've got two right triangles, I should say, that are put together. We need to solve it in a smart way. I notice that this triangle, I know two sides, and I'm missing one, whereas the other triangle, I actually am missing two sides. So we're going to start with that triangle outlined in green. We'll do 1 squared plus 5 squared equals x squared, and we'll figure out what x is. And then we'll use that to solve the second triangle. That's our new hypotenuse. Now, you definitely don't want to use a calculator here. Because as soon as you type this into the calculator and get a decimal, when you perform your next step for the next triangle, you're going to end up, if you round it off in your calculator, you're going to end up with an inaccurate answer at the end. It would be better just to keep x as, keep x as being the square root of 26, because when we square that, now the square root and the square cancel out here, and we just have y squared plus 26 equals 36. Again, we get the y squared by itself, take the square root, and we're good to go on. So we see that chapter 1 and chapter 4 are absolutely involved here, so we can't just move on from them. We need to go back and review if we need extra help with those. All right, section C. Now this is something that you might not be used to, but it's really easy. So usually with the Pythagorean theorem questions, we start off by knowing that there's a right triangle. We're told it's a right triangle. It's got the little box in that angle. And then we're given, whatever, two sides, and then we're asked to figure out, hey, what is that third side? However, it also works backwards. So here's a triangle. It's not drawn to scale. Is it a right triangle? So we can check, do the sides exhibit this property, that two sides, when we square the two sides and add them together, do we get the third side squared? And it's not a huge guessing game, because if this were a right triangle, which side would have to be the hypotenuse? The longest side, 97. So we can just grab a calculator and we can check, is 65 squared plus 72 squared equal to 97 squared? Indeed it is. That means that this was a right triangle the whole time. It had a secret right angle right there. I know it didn't really look like it, but it was a right angle all along. So that's what we mean by the converse of Pythagoras' theorem. It's testing whether a triangle had a right angle or not. D. D is all about shortcuts. So technically this is an optional section to think about, but I think it's really important. So we have this concept of a Pythagorean triple, or I'm used to calling them triplets, but whatever. And that's just a set of three integers which would work in the Pythagorean theorem, which exhibit the property that one number squared plus a second number squared equals the third number squared. And so one example of it is 3, 4, 5. That's probably the most famous Pythagorean triple. And then the two next most famous ones are definitely 5, 12, 13, and 8, 15, 17. And then you've also got 7, 24, 25. That's one that I have memorized. And those are actually the only four that I have memorized. But there's a lot more. In fact, I just used one on the previous screen. It was the 65, 72, 97 Pythagorean triplet, although I wouldn't expect anybody to have that thing memorized. And whatever, you can look on any number of websites and see a whole list of a bunch of these things. But I think you should really memorize the first, like I said, these first four I would definitely try to commit to memory. But here's the thing that makes Pythagorean triplets so great. Memorizing one of them actually gets you access to infinitely many more. Okay, so I'll show you what I mean. So we'll start with the 3, 4, 5, which is what the Wikipedia called a primitive Pythagorean triplet. You don't need to know that word, of course. So first of all, let me erase that 5 for a second. I know the 3, 4, 5. I have it memorized. So I'm not going to bother showing the work of 3 squared plus 4 squared equals x squared and then adding things and taking the square root. I know that the hypotenuse has to be 5. Now, what if I see another right triangle which has legs of, say, 6 and 8? I don't need to do 6 squared plus 8 squared equals x squared, because 3, 4, 5 is the same as 6, 8, hopefully you see the pattern here, 10, because it's just all three of the sides all multiplied by the same value, in this case, 2. Likewise, if I saw a hypotenuse of, say, 25 and a leg that would be 15, I don't need to get out my calculator and start squaring large numbers, because I notice that 25 is 5 times 5. 15 is 3 times 5, which means that the other leg is just going to be 4 times 5. And that's going to be 20. We can also be a little fancy with, say, smaller numbers. Like, let's say I had 0.75 and 1. And this one's maybe not as obvious, but it's better if you think in terms of fractions. 0.75 is the same as 3 over 4. 1 is the same as 4 over 4, which means that my hypotenuse is going to be 5 over 4. So this is why we memorize the triplets. So many questions that you see in textbooks, and believe me, on my quizzes and tests, and later on when you get to like SATs and stuff like that, these are out there, and they're testing to see whether you, the student, is able to like memorize some basic math facts and then apply them to I don't know, to more challenging situations with bigger numbers in an efficient way. So it's much more efficient to see this pattern and apply it than it is to have to square gigantic numbers. I mean, like if I had a triangle, you know, that was like 3, I don't know, with like a whole bunch of zeros and then 4 with a whole bunch of you see what I mean? Like the calculator might not be able to fit in all of these zeros, but we should be able to get the answer. It's going to be 5 with a whole lot of zeros. Obviously, I was lazy here. I meant for them to be the same amount of zeros for all 3 of those cases. So that's triplets. It's a huge time saver, and I really, really, really want you to memorize at least these 3. And preferably, it would be nice if you see that one too. And I don't know, memorize as many as you can off that Wikipedia page that I showed before. Like I said, they're really helpful. We're almost out of here. Sections E and F are just about problem solving. So just like with any geometry problem, the first thing you're going to want to do if we have like a word problem is try to draw pictures so that you can visualize it. Don't worry about drawing things to scale. Just make sure that it's neat and the things are labeled. Okay, step 2, we're going to like mark anything that we know. So we want to like, what is the right angle? What are the known lengths or whatever else? We're going to throw some variables in there. Step 3. Step 4, we're going to use the Pythagorean theorem. Step 5, solve the equation. Oh my gosh. And then, hey, 6, if it's necessary, if we have like context to a word problem, it's really, really nice to write our answer in sentence form. We'll look at like a little bit of this, but I'm not going to do too much because, as always, word problems could be about anything. So it's not like I could show you every possible question that might come your way. But I do want to point out there's some facts about various geometrical shapes that are going to really help you get through some of these problems. So something you should know, in a rectangle, if we draw in a diagonal, we have then made a right triangle. Right? Actually, we've made 2 of them. So that's like you may need to draw in a diagonal to create a right triangle so that you can use it in the problem. If we have a square or a rhombus, what's a rhombus, by the way? A rhombus is like kind of like a slanted square, so all 4 of the sides are the same. It is equilateral, however, it is not equiangular. But in both a square and a rhombus, if we draw in both diagonals, they will bisect each other at right angles. So in the case of the square, we've created 4 right triangles, and all 4 of them have congruent legs. Whereas with the rhombus, we will still have 4 right triangles. However, they will not have congruent legs because these 2 are the same as that diagonal has been bisected, but this is the longer diagonal. So the 4 pieces we've created there are not all equal. And then finally with triangles, whether it's an equilateral or an isosceles triangle, if we draw in an altitude, and an altitude is just a line going from the vertex, like so the spot on top in these 2 cases, and which is perpendicular to the base. That's what an altitude is. It always has to be perpendicular to the base. It's called an altitude because, like, if you were to drop something from a height, from an altitude, you know, it would drop straight down to the ground in a manner that it would be perpendicular to the ground. But anyway, that altitude is going to bisect the base at right angles. So again, we have 2 congruent pieces here and 2 congruent pieces here. All right, so that's all going to be really helpful for solving word problems that have to do with the Pythagorean theorem. Again, these lines that are dotted in these images are ones that you might have to draw in. Those are auxiliary lines that will not necessarily be in the picture at first. Okay, so like here's an example. All we would be given here are these words, so we'd have to draw the rhombus first of all, and then we're told that the diagonals are 6 and 8. So the short diagonal would be 6, and then the long diagonal would be 8. But we know that they bisect each other, and that's why we're given the lengths of 3 and 4 in a right triangle. And then we're asked to find the length of one of its sides. Well, you can do all this work if you want to, but this is a Pythagorean triplet, so if I have legs of 3 and 4, I know that the hypotenuse needs to be 5. And finally, section F is just like more word problems that have to do with navigation. So like it's important for you here to know north, south, east, and west. And there's like a whole lot of ways that people use to memorize the order of these things, like never eat sour watermelons or something like that, like going around in a circle, but I don't care. Just, you should know how to read a map, people, all right? So anyway, here, a yacht is sailing 23 kilometers south and 18 kilometers east. So we're going to draw a right triangle. Let me see, it's starting at wherever, an arbitrary place. We go 23 south, 18 east. Oh, I get it. It's a right triangle. So we use the Pythagorean theorem, and then we figure out how far away it is from where it started. Not a challenging thing once you figure out what the picture is you need to draw. One more. So we have two people leaving the same point at the same time. This is a classic. One person goes in one direction, so the man's going east, and then the sun's going south. So we draw this in. So they're both starting from here. The man's going east, the boy's going south. Now we're given in this problem their velocities. The man's going 16 kilometers per hour, but he's traveling for 4 hours. So we multiply 16 by 4 to get the distance, which is 64. And then likewise, the boy is riding at 20 kilometers per hour, again for 4 hours, so that gives him a distance of 80. And then from there, it's just the Pythagorean theorem, and we solve it. Bonus math time. Did you think I was just going to let this go? Did you see this picture when I was on the Wikipedia page earlier? We've also got this other cool thing down here. Let's look at these. This is it's called a scatter plot. And all this is they're laying down coordinates for the legs of a primitive Pythagorean triplet. So the first Pythagorean triplet was 3, 4, 5. So there's a coordinate here somewhere right over here at 3, 4, and there's another one at 5, 12, and another one at 8, 15, and 7, 24, etc. And they've plotted this for, I don't know how many this is, a whole lot of them. And it's just this like beautiful geometric shape. I just think that's really cool. I have no idea what's going on here mathematically, but it just like, doesn't this look so neat? Like we have these like kind of arcs happening, and then things are happening along straight lines, but these lines aren't connected. I want to emphasize that. There's gaps in between them. We're just zoomed out so far, and there are so many points that are filled in that it looks solid from here. I just thought that was really cool. And then this other picture was really neat too. I have even less of an idea of what's happening here. Something about the I don't know. You can go read it yourself. But I just thought that was really neat. There's also a really great video by one of my favorite YouTube channels, 3 Blue 1 Brown, about visualizing Pythagorean triplets. But that requires you to understand complex numbers, so I feel like that's probably a little much for you right now. But I'll put a link down below in case you've seen them before, and maybe you'll appreciate what he has to say about it. So that's it for this one. As we can see, looking ahead at the next two sections, section G is about circle problems. So that's going to have a whole bunch of extra geometrical theorems that some of which you might not be familiar with at first, but it still all has to do with right triangles, just in more complicated situations. And then we'll also see how we can apply the Pythagorean theorem, not just to two-dimensional problems, but also to 3D problems within, like, space and stuff like that. And truthfully, we can even extend it beyond that, but you know what, that's a conversation for another day. So anyway, that's it. Catch you next time. I am home.